Okay, you can see on the screen here a standing wave. And our goal in this problem is to do the problem algebraically and show that the numbers that we get here for the frequencies actually match what is predicted according to all the wave equations we've been talking about. So first, let me just show you here. This mass is hanging freely. This is a 200, let me make sure it's a 200 gram mass. 200 gram mass. And then, so if I get this, right, that's pretty close. I don't know if you could see this very well on the screen, but we see a pattern here where there's a node here, a node here. Notice halfway in between is an antinode. You can really see the string vibrating when I touch it, right? And so if you leave this system alone, we see a standing wave setup. And what's happening here is this is the oscillator wiggling up and down. And I believe, let's see, I'll point out just for reference, looks like we're at 57 hertz is the frequency, which gives us this 3-bump pattern. So we'll keep that in mind and we'll come back to that. Let's go to the board. Give me just a second. Let's see, let's go to board 1. All right, so we're looking at workbook problem 16.15, just page 36, volume 3. We're going to do this algebraically, then we can go back and see if we can confirm that F3 should really be 57 hertz. Okay, so the givens in this problem, we know the hanging mass. That's something you can put on a balance really easily. We know the length of the string. I measured that to be a meter. I had a meter stick on the table. I could show you that again at the end of the video. But yeah, the length that I chose happened to be about a meter. And the mass density, we call that the linear mass density of the string. Remember the units. That's in kilograms per meter. So basically you take a length of the string. I think I had Angus pull out 2 meters of string and then just get the mass of it. And that gives you the linear mass density. This particular string is nice because it shows up well and it doesn't stretch a lot. If you have an elastic cord, things get a little bit trickier because if the cord can stretch, that's going to change the linear mass density as it stretches. So that would be a little bit more difficult problem, but it's not insurmountable. We can discuss that some other time in lab or something. So let's start with this. What are some things we know about this type of problem? Well, I guess we should just start with part A of the problem, where it touches the pulley. So here's the pulley. At this point, right there, is it a node or an antinode? If you want to pause, go ahead. 1, 2, 3. Here we go. This is a node. And I'll just use capital N for that. All right. That is a point with minimum displacement. Notice there's no displacement right here. The string can't go up or down because the pulley is preventing that. So that was part A. This is a node. Part B, what about the spot where it touches the oscillator? And if you saw that in the screen, it made this kind of 3-bump pattern. And we see that this point right here must also be a node. Now you might be saying, wait a minute, this oscillator is wiggling up and down. That's what makes the wave appear. It's not motionless. It is being displaced vertically. You're absolutely right. But in terms of wave reflections, we know that when the string hits here, this is going to cause the wave to reflect and invert. So in that sense, we're viewing this as a node. And then if you want, I'm going to just sketch in. Let me see what's part C. Oh, okay, we'll do that. Whoops, wrong problem. Okay, so parts A was this is a node. Part B, this is a node. I'm going to sketch in the pattern of nodes and antinodes here. These two are also nodes, spots where the string was not moving because the wave traveling this way and the wave traveling that way always cancel out at these 2 points. And then these spots here are antinodes. This third spot too. So we see 3 antinodes, 4 nodes in this case. Part C of the question asks, are the boundary conditions mixed or matched? Well, in this case, here's one boundary condition. It's a node at one end because it's essentially fixed from an inversion standpoint for the reflection. Here it's also fixed, right? So we see both conditions are fixed. Part C, we have matched boundary conditions. All right, let's see what part D is. What is the relationship between the length of the string and the wavelength? Okay, so for this particular case, we see, I like to, when you have matched boundary conditions, I like to think in lambda over twos or half wavelengths. So I see that I have 1/2 wavelength, 2/2 wavelengths, 3/2 wavelengths. So I see that an integer number of half wavelengths fit on the string. So we could write that as an integer times lambda over 2. An integer number of half wavelengths should equal the length of the string. There we go. Now, if we wanted to flip this around, I guess you could solve this for lambda. Why don't you do that really quick? See if you can beat me to it. So what is lambda? Let me make sure I didn't screw it up. 2 comes up top and yeah, all right, so we're good. So this gives you, if you wanted, you could even put a subscript n on here. This is the nth wavelength, the wavelength of the nth harmonic. Now in this case, this particular example, n was 3. How do I know that? 3 half wavelengths fit in here. So we're looking at the third harmonic. Sometimes you would call that F3. All right, let's see what part E is. Derive an expression for the nth frequency, f sub n, in terms of all these symbols. Okay, so here's where we're going to go with this. I know that V is equal to F lambda. All right, V is wave speed. So let's make that clear. However, I know from experience, wave speed is given by tension over the mass per unit length. So if I could just figure out the tension, oh wait, I know the hanging mass. Now in this case, there's mg down, there's tension up, and the acceleration is 0. So in this, that G looks a little sloppy. Yeah, it's a little better. Let me get this glare off of here. All right. So in this particular case, notice we could plug in what capital, the tension happens in this case to be capital MG. If this was accelerating an elevator, that'd be a little bit different, right? You could literally take this whole apparatus, stick it in an elevator and make it accelerate, and that would change the tension and require different frequencies if you're accelerating up or down versus at rest or at constant speed. Anyways, let's finish this thing out. So tension, I hope you agree that tension is just capital MG. Notice it's important to write your symbols well. Mu looks like a U, right? You write a U and then you add a line versus capital M versus little m. Make sure you're writing your symbols correctly. Let me get an eraser for that. Let's get this done. Now at this point, I might as well solve for F. You're erasing me, that's fun. Now I'm going to plug in what lambda n is. If I use lambda n here, I'll get frequency n. Meaning I'll have if I use the harmonic number in the wavelength, this condition that we just derived right over here, that will give me the frequency associated with that harmonic number. Well, in this case, that's just going to flip it upside down. N over 2, plugging this in. N over 2L, and then I still have mg over mu. All right, so that's the algebraic result. So that's part D. Or, oh, whoops, that was maybe part E or something. I think this was part E. So all of this work right here was part E. Okay. So now, why don't we take a minute? If you wanted to stop the video here, you can, but I just want to see if this matches up to the results that we predicted. So let's go to board 2 really quick. Come on now. Okay, I happen to have the numbers recorded up there. Angus again got that number for mu yellow at the top right, using just 2 meters of string and a balance. And let's write down what we saw here. F sub n was n over 2L, green, times the square root of capital M G over mu. And I do think it's worth actually plugging in the numbers here, because you'll see a lot of times when you measure string, it's a very low density. So notice we have grams here, we have grams there. We got to think a little bit about how our units are going to work out when we plug stuff in. All right, so in this case, we wanted to use, I think we were using n equals 3. So let's see what happens when we plug in all these numbers with n equals 3. So F3, we find 3 over 2 times 1.00 meters. You can race ahead of me. I'll catch up in a minute. Now, in this case, I believe we can actually leave this in grams and that in grams, but I'm going to include the units here just to make sure I don't screw it up. 200 grams, I'm going to assume that's good in the third sig fig, times G. That's about 3 sig figs. And then the mass per unit length, 1.351 grams per meter. Now let's check the units inside. To be clear, this G is grams. And so is that G. And so notice, we can actually have the grams cancel out. We have this meter, it's a 1 over meter, right? So that's the same thing as multiplying by meters over grams, the grams cancel. Notice we get meters squared here. Let's go a little bit further. Meters outside of the square root, if you brought that in, would be meters squared. This cancels that, and notice we get the units of square root of 1 over second squared. That's 1 over seconds, which is hertz. So we do get the right units. So we're going to get 1 over seconds, which is the unit of hertz. And I'm going to get my calculator. Go ahead and do it. See if you can beat me. First problem of the day. We'll see how slow I am. Okay, so I'll do that square root first. Square root of 200 times 9.8 divided by 1.351. Then I need to multiply that by 3 divided by 2. I got 57 and change. Where's my markers? There they are. We'll say probably around 2 sig figs. I think this was something like that. So this actually matches what we saw. Now, before you just turn off the video, I'll have you guess a couple of things. Let me get back onto the demonstration and show you that we really did have a meter and this was 54. Is it this one? Whoops, wrong one. Come on. There we go. All right. So let's take a look at this and have some fun. Right here, you can see that this is 57 hertz. And so I'm going to show you that as I change the frequency slightly away from that number, we should see the pattern disappear. Right? And here's an interesting thing. For matched boundary conditions, we saw 57 was n equals 3. Well, think about that. That was 3 half wavelengths fit on this length string, which is about a meter, as you can see. Okay. So what if we divide that number by 3? That would be 1 half wavelength. 57 divided by 3 is 19. Let's go down to 19. Give me a sec. It's a little lag here. Oh, starting to form. Notice that's a 1 bump pattern. Can you see that on the screen? Hopefully you can a little bit. The n equals 2 shows up a little bit better. So, right, 57 divided by 3 was 19. Now we have our root frequency, or fundamental, is 19. So what number would we have to use for the frequency to get the n equals 2 harmonic? If you want to take a guess, go ahead. I'll tell you the answer in 3, 2, 1. We take the fundamental and double it for matched boundary conditions. Again, this is for matched boundary conditions. Mixed is a different problem. We'll do that next. So let's go up to about 38. Pattern disappears. The waves are constantly being destructive. We're starting to see a 2 bump pattern appear. Getting stronger. There it goes. This is at about 37, 38, pretty close to 2 digits, at least that's what we see. We see so that's kind of fun. Now, one last little bonus. You see that there's a section of the string over here that's much shorter. Think to yourself, if I wanted to get a standing wave over here, what has to happen to the frequency? I'll give you the answer in 3, 2, 1. It's a much shorter wavelength, but it's the same string tension. So V, wave speed, is the same because string tension is unchanged. The wavelength goes down because it's much shorter. Lambda over 2 now has to fit onto this string. So you're going to need a much higher frequency. Let's crank it up. We may have to go up to here. And in case you're wondering, listen. What is this mechanical oscillator? It's essentially a speaker. And then you just stick a stick on it and it wiggles up and down. So if you wanted to make one, you could. Notice we're getting a standing wave on this side now. Think, which harmonic is this? 3, 2, 1. It's the first harmonic because we only see one big bump. 1 lambda over 2 fits on this tiny string at about 85, 86. If you're curious, that string length is about, I don't know, maybe 25 or 24 centimeters. It's hard for me to read right here, but you can use that to check your math if you want. So that's pretty much, we beat that to death. Let's call this video good. I guess as a fun puzzle, what's the lowest frequency to get a standing wave on both? Ooh, you could contemplate that.